Hello and good afternoon, everybody. So today I will record it again because yesterday I recorded the whole class, but unfortunately there was no audio. So that means you could not hear me. So I have uploaded the PowerPoint, which belongs to this video on Moodle. And here, when I'm done, I will upload this on YouTube and also on Moodle. And then you can watch the video and you can just parallel, you can then go through the PowerPoint, which is uploaded on Moodle while you are watching the video. Yeah? Okay, our first class deals about Earth's materials, and Earth's materials, these are the minerals and the rocks. So going now to our next slide, here we have a very nice hand specimen with a lot of crystals, and these crystals, which you can see here, these are quartz crystals. Yeah, you can just see it here on the hexagonal shape. So these are our Earth's materials, and these Earth's materials consisting of minerals and rocks. So about Earth's materials, I mean, I'm just starting on a very easy base because I don't know what you have done before. And so we are starting here just from scratch. So now something about Earth's materials. All Earth's materials are composed of atoms, and these atoms are bound together, yeah? And that you know by now. So, and minerals are composed of atoms, and these atoms are bounded together, and the minerals are the building blocks of the rocks. So that means every rock consists of a certain number of minerals, or the mineral itself forms by itself the rock. And a good example here, therefore, is obsidian. Yeah, obsidian, you know, that is actually SiO2. SiO2 is a quartz, and an obsidian is a rock. And this obsidian consists of quartz. So, and rocks are composed of minerals, and they record in various geological processes. So, I mean, what can we do with such a rock? So, we can sample this rock in the field, and we can make a thin section, and we can investigate this thin section under the microscope. Then we can identify the different minerals. Then we can make suggestion what type of rock it is. And then using different mineral, chemical and geochemical methods, we can figure out under which conditions this rock is formed and when it was formed. Yeah. So, and therefore we can these rocks are then witnesses for the whole geological processes which we can observe on this planet. So the lecture outline therefore is we will at first discuss what minerals are, yeah? Second, we will talk about the structure of matter. I will explain this then later on more in detail when we are coming to point number 2. Then we have number 3, the formation of the different minerals. Then we have number 4, the classes of the rock-forming minerals. We have number 5, the physical properties of minerals. And we have number 6, what are rocks, yeah? We are continuing with chapter number 7. We will discuss there the rock cycle. And the rock cycle that describes the interaction between the plate tectonic and the climate system. Number 8, we have the concentrations of valuable mineral resources. And these are the 8 points, and now we are starting with our first topic, what are minerals? So what is a mineral, yeah? Minerals, and that I told you just before, are the building blocks of the rocks. And secondly, geologists, they define minerals as a naturally occurring solid crystalline substance, usually inorganic, with a specific chemical composition. Yeah, that is the definition of a mineral. Yeah, so and this definition is a little bit old-fashioned. Why is it old-fashioned? It is old-fashioned because if you are looking for water, yeah, ice is regarding this definition a mineral. Yeah, it is solid, it is a crystalline substance, it is inorganic, and it has a specific chemical composition. So what happens when the ice melts? Then we have water. So, and water is then not longer regarding to this definition, water is not longer a mineral, because water is not solid. And it is also not a crystalline substance, but chemically it is still inorganic, and it has the same chemical composition like ice. So, and therefore, we are using in phase petrology not the definition of a mineral, or we are not talking about mineral, we are talking then about phases. So, and the phase can be solid, it can be liquid, and it can be steam. So, now next definition about what is a mineral. So it is occurring in nature, that means we can find it in nature. It is a solid crystalline substance, and this substance contains of atoms, and these atoms are arranged in an orderly pattern. Usually they are inorganic and not a product of living tissue. And they have a specific chemical formula and a unique chemical composition. So every mineral consists of different atoms. They are arranged in an orderly pattern, and we have therefore a chemical formula for every mineral, and every mineral has its own chemical composition, yeah? So then I have here some short questions for this chapter. You can go through all the questions, then you can try to answer the question and send it back to me, and therefore we have the first assessment, yeah? So, and the regarding literature is the textbook Understanding Earth. So, and there are several versions of Understanding Earth in the library. So you can then just go through this textbook, and then you will be able to answer all these questions. So coal, for example, is a natural organic substance that forms from decaying vegetation, and therefore it is not considered to be a mineral. However, when coal is heated to high temperatures and buried under high pressure, it is transformed into the mineral graphite. Yeah? Why is it then that coal is not considered a mineral, but graphite is? So, and therefore you can now check some textbooks, or you can check the internet, and then you can just look for an explanation for this reasoning. So now we are coming to point number 2, the structure of matter. So as everybody knows of yours, the atom is the smallest unit of an element that retain the physical and chemical properties of that element. So that means we have atomic nucleus, and this atomic nucleus consists of protons and neutrons. Electrons could move, or electrons, they are forming clouds, and these clouds are moving particles and they are surrounding the nucleus. So, and we have now, or I will now show you the example using the carbon atom C. So we have here in the middle the atomic nucleus, and then this light colored bluish sphere is the electron cloud. So, and there I'm showing you an example using the carbon atom, yeah? Because we discussed just before, or we talked about the carbon atom, yeah, why coal is not a mineral and graphite is mineral. And if we are putting this graphite under ultra high pressures, then we are forming from this graphite and diamond, yeah? So when the carbon atom has this electron cloud, the atomic nucleus, and carbon has 6 electrons, yeah? So, and now we are watching the whole thing in 2 dimensions. We have here the proton, these are the reddish bubbles. We have the neutrons, these are the light bluish bubbles. So, and then we have the electrons, and they are swirling around the atomic nucleus. So, and the nucleus, or this nucleus consists of 6 protons. So that means the electron is negative charge, the proton is positive charge, and the neutron is neutral. And we are having then the 6 neutrons, and as I just told you by right now, they do not have any charge. Now we are coming back, or now we are coming to the isotopes. So what are isotopes? Isotopes, these are atoms of the same element with different numbers of protons. So for example, the carbon atom C has typically 6 neutrons and 6 protons, and therefore we are calling it C12. And if you are watching the periodic table of the elements, then you can find C12. So, but there are also small amounts of C13 and C14 around. And maybe you know from your classes in the secondary school, there you have probably done in biology, or you have discussed in biology, the C14 method. And with the C14 method, you can use this for age dating. And for example, C14 can be used for ages up to 40,000 years, or 60,000 years, and that is then good enough if you like to date, for example, older elephants, or I don't know. So then when we are talking about, we have atoms, and these atoms are bounded together, and therefore they are forming then the minerals. So and between the minerals we have then chemical reactions, yeah? We will discuss this later on in our later classes in petrology and petrogenesis. There we have then a chemical reaction. That means one mineral is reacting away and the other one is formed, for example. And there we have the interactions of atoms of 2 or more elements in a certain fixed proportion. So we have there chemical reactions between our minerals. So when this chemical reaction will take place due to pressure and temperature changes, and that is pressure and temperature changes are caused, for example, due to the plate tectonic processes. That means the movement of our plate. So, but that is not the only thing. For example, it is you have also pressure and temperature changes when the melt somewhere rises up, or even if you have a meteoric impact, yes, then you are increasing the pressure within a very short time to incredible pressures. So, and therefore you will have then a certain mineral reaction will then take place. So here, for example, we are just using here now a totally simple example. We have two hydrogen atoms plus an oxygen atom, and then we are forming H2O. So in the H2O, that is water, yeah, or ice, can also be steam. Or we are going back to your daily soup. What are you putting inside in your daily soup? You are putting salt inside, and then you have sodium plus chloride will form sodium chloride, yeah? Here you do not have now mineral reactions between minerals. Here we have then just the addition of certain elements, and these certain elements forming then the mineral. Or in the case of water, we are forming a phase, yeah? So, and then we have chemical compounds that are minerals formed by. So, what are the chemical compounds? We have electron sharing, yeah. I mean, we must hold these elements together somehow that we can form a mineral. So, and that can be done through electron sharing, or it can be done through electron transfer. So, for example, here we have again the carbon, yeah, carbon atoms. So, and then we have in the middle here this bigger bubble, that is the nucleus, consists of protons and neutrons, and we have the electron clouds around. So, in these electrons, they are bonded with each other, and therefore you can then form the mineral graphite, for example, yeah? This is then electron sharing. Here they are sharing here the electrons in this cloud. So, in carbon atoms, and here we have the example of carbon atoms in a diamond, yeah? I told you this just right now or before. We have carbon atoms, or at a low pressure we can have carbon atoms in coal. Later on we have graphite, which is then a mineral, and if this graphite undergoes then high pressure conditions, then we are forming a diamond out of this graphite, yeah? So, or we are going back to our daily soup. We have a sodium atom, and that has one electron in the outer shell, yeah? You can see here, we have here, that is the electron transfer. We have here the one electron in the outermost shell. So, and then we have here chlorine, and there chlorine, and there we have 7 electrons in the outer shell. So, and then we there is then one gap, there is one missing, and that means we are dealing then, or electrical attraction will take place. So, in the sodium and is the cation, and the chlorine is the anion, and then they are bounded together, because we have one electron in the outermost shell from the sodium and one gap in the chlorine, and then this one electron in the outermost shell from the sodium will fill the gap in the chlorine, and then we have our salt, the halide. And the halide, that is the stuff which you are putting every day in your soup. So that means sodium plus chlorine will give then sodium chloride, and that we are calling a halide. So in such a halide, here we have is cubic. So and here each sodium ion that is circled in red is surrounded by 6 chloride ions, and these are the circles which are in yellow and vice versa. And then you are forming here this ball model. Next one, yeah. This is a ball and stick model. Here you have the sticks, here you have the balls, and here we have just the ball model. Yeah, that shows us theoretically, or not theoretically, it was really like this, a sodium chloride crystal. So, and on the last figure on the right hand, you can see the table salt, the halide, and you can see very nicely the crystallographic system which forms a cube, and that is then your halide, yeah? So that is then the so-called electron transfer. We have sodium plus chlorine will form halide. Number 3, we are talking now about the structure of minerals. How do minerals form, yeah? So minerals can be formed under different conditions, yeah? Most of the minerals are formed by crystallization from a melt, yeah? So, and these are then the so-called igneous rocks or volcanic rocks. We have a melt, and it melt cools down, and then you are forming your minerals out of the melt by crystallization, yeah? How this works in detail, we will then discuss in the 3rd year and in the 4th year. So, and that means when we have the crystallization out of the melt, that means atoms coming together in a proper proportion and in a proper arrangement, yeah? That is now for you as a 2nd year student actually everything what is now important to know. So, and therefore we are talking about electrical charges of the atomic ions. So we have the cations, they are positively charged, and we have the anions, they are negatively charged, and then we have plus and minus, and these atoms going then together like a magnetite, yeah? You know about magnetism, yeah? You have a positive side, a negative side, and then they are clutching together. So in these atomic ions, they are arranging themselves, and that depends strongly on the charge, of course, and on the size. For example, sodium is a positive at one time positive charge, chlorine is one time negative charged, and the atoms are nearly of the same size, and then they are finding together, yeah? So, and therefore we have the forces of electrical attraction between the protons, which are positive, and the electrons, which are negative, and that hold minerals and other chemical compounds together. So that means we have here covalent bonds, we have also ionic bonds, and we have metallic bonds. And here in this nice diagram we have some most important cations and these most important cations are those cations which can be found in the most dominant or prominent rock forming minerals. So for example, there is silica, yeah, that is Si4+, and I mean most rocks are silicates, and therefore silica is there very important. So then and silica is a very small bubble with when you are looking here at the radius. So then we have aluminium, it says 3 plus, the bubble is a little bit bigger. Then we are coming to the iron, Fe3 plus, we are having then also a bigger bubble. Then next one is magnesium, Mg2 plus, then we have iron, Fe2 plus. Sodium is just one times positive charge. Then we have calcium with 2 times positive charge. And potassium, which forms then a very big bubble, and that is also 1 time positive charged. Then we have the most important anions below. We have, of course, the oxygen, yeah, which is 2 times negative, the chloride 1 time negative, and the sulfide also 2 times negative. So now, when do minerals form? So that is during cooling of a molten rock, for example. Yeah, we have a melt and there is a molten rock, and then this melt cools down, crystallization processes will take place. Atoms finding together due to their size and due to their electron charges, they are finding together, forming different minerals. And these minerals are crystallizing then out from the cooling melt. So, and this is the most common process which leads to the formation of minerals. Yeah, but that is not the only process. We have there also some other possible processes. So, and one other process, that is during the evaporation of water. So that means during the evaporation of water you can form salt ore deposits or gypsum ore deposits, yeah, or phosphate ore deposits. And you can do this or repeat this also very easily by in your kitchen using a kitchen experiment. Yeah, you are putting water, you are putting some water in a pot and making an oversaturated brine. That means you are putting salt inside. So, and then you can boil this water, and then you are boiling it and boiling it. You have then the phase transition from liquid water into steam. The steam will become removed, and at the end you will find at the bottom of your pot you can find or you can observe some salt crystals, yeah? So when these things are all happen, upon changes in temperature and pressures on existing minerals. Or here we can also talk then about metamorphism. We have a rock and we are changing the pressure and temperature conditions. Then it leads to mineral chemical reaction, and one mineral will become consumed and another one will be formed. So number 4, we are talking now about classes of rock forming minerals. So and here we have different chemical classes of minerals. We have the silicates, and these are the most dominant group of minerals, yeah? And they are silicates because they contain oxygen and silica, yeah? Therefore we are calling them silicates, yeah? Then we have carbonates, and they contain carbon and they contain oxygen. Then we have oxides, and they contain oxygen and metallic cations. So then we have sulfides, and they contain sulfur and metallic cations. And we have sulfates, they contain then SO4 and metallic cations. Here we are continuing now with the chemical classes. We have also halides, and you know the halides by now, that is salt, yeah? And they contain then chlorine, fluorine, iode, or bromide. Then we have hydroxides, and hydroxides containing an OH group. Then we have also native elements, and the masses of all the same element is metallically bounded. So in native elements, this is for example gold and copper, yeah? Or also carbon, yeah? So here we have now a silicate tetrahedron, yeah, the formation of silicate minerals. We have the silicate ion, that is SiO4 minus. So, and in the middle here we have our silicon atom, and here we have 4 oxygen, yeah. Here we have 4 oxygen, and the oxygen is 2 times negative charge. The silica is 4 times positive charge. If we are making here a charge balance, then we need 4 gaps from our oxygen to host the silica, and there are still 4 gaps from the oxygen are left, and these 4 gaps we need for the connection to other tetrahedrons, with other tetrahedrons, yeah? So, and here it's then written, the silicate ion forms tetrahedra. So, and now we are going to the next picture to the right. We have here the quartz structure, yeah? Then you have always this big silica bubble inside, and these reddish bubbles, these are the oxygen, and one tetrahedron is connected with another tetrahedron in the quartz structure, and quartz is a framework silicate, yeah? So, and here we have quartz, or here we have the definition, quartz is a silicate polymorph. So now, what is a polymorph mineral? A polymorph mineral is a group of minerals which having the same chemical composition but different crystallographic symmetries. So, and if you are looking at the mineral quartz, we have the alpha quartz, that is just a quartz which you can find here on the ground. We have the alpha quartz, we have beta quartz, we have cristobalite, we have tridymite, and if you are going to higher pressures, then we are forming a coesite, and at very high pressure conditions we having then the modification stisovite. So, and as I told you before, the tetrahedras are the basic building blocks of all silicate minerals, and about 95% of all the Earth's minerals are silicates, yeah? So here I have now some other short questions for this chapter, which you can solve while you are at home. So first I would like that you are drawing a simple diagram to show how silicon and oxygen in silicate minerals share at electrons. Yeah, you should be able to do this by now. Now we will discuss a little bit talk a little bit about the different types of silicate minerals. So we have isolated silica tetraedras. Then we have single chain linkages. We have double chain linkages. We have sheet linkages. And we have framework silicates. So at the beginning we have here, for example, the mineral olivine, and the mineral olivine is the most dominant mineral in the Earth's mantle. It has the chemical formula, it depends when we are talking about the forsterite end member. We have Mg2SiO4, or we have a mixture between forsterite and firelite, and then we have MgFe2SiO4. So the cleavage planes and the number of cleavage direction in olivine, that we have one plane, and the silicate structure that we are dealing here with isolated tetraedrons. And here on the right side we have a typical hand specimen of the mineral olivine, and these are these very nice greenish minerals, like you can see it here. So then the next group, which is shown here, that is the pyroxenes. The pyroxenes can be subdivided in orthopyroxenes and clinopyroxenes. Here in this example we have an orthopyroxene which has MgFeSiO3, or you can also write it down as MgFe2Si2O6, which I would prefer. So then we have here two planes, and these two planes crossing at 90 degree or roughly 90 degree. To be totally correct, they are crossing each other in an angle of 89 to 91. So, and here we are forming then single chains of tetraedrons, and very on the right hand we have a hand specimen. So now next pictures, we have the amphibole. We have here the chemical formula of a clinoamphibole. And this we are distinguishing, when we are talking about amphiboles, we are also distinguishing between clino and orthoamphiboles. We will discuss this in the third year, why this is. So, and here we have, for example, a clinoamphibole, and this clinoamphibole is an actinolith. We have Ca2MgFe5Si8O22OH2. Here we have two planes, and they are crossing at an angle between of 60 and 120 degree. To be totally correct, it should be an angle, the angle should be 56 and 124. So here the amphiboles are forming double chains, that is the arrangement of the tetraedrons. And here, very on the left, on the right hand, we have a nice picture from a hand specimen of amphibole, yeah? So then we have here the micas. The micas are sheet silicates. We have dioctaedral micas and trioctaedral micas. That is then also subject for the third year to distinguish them more in detail. So, but we have a white mica and the black mica. The black one is the biotite, the white one is the muscovite, or here we have just one white mica. You can have different white micas, yeah, but here we have the most common one, which is a muscovite. And this is an aluminium bearing mica, yeah? Whereas the biotite, these are dark micas, and they contain less aluminium, but instead of the aluminium we have here magnesium and iron inside. Here we have also one cleavage plane. We are forming sheets of tetrahedrons, and here very on the right side we have a nice picture of a hand specimen, and these biotides, they are forming always such booklets. So then we have the feldspars, and the feldspars are three-dimensional. They are the arrangement of the tetrasilicates. That is a three-dimensional framework. You have the orthoclase feldspar, which is potassium aluminium Si308. So that is just a K-feldspar. And you have the plagioclase feldspar, which is calcium, sodium Al Si308. So here we are dealing with two planes, and these two planes are crossing each other at an angle of 90 degrees. As I told you before, we have here the formation of a three-dimensional framework, and very to the right we have a nice picture from an hand specimen. So here now again some short questions for this chapter. So diopside, a pyroxene that has the formula calcium calcium magnesium 2 Si2O6. That is the clinopyroxene, and there we have the mineral chemical formula. So and the question is, what does that tell you about its crystal structure and the cation substitution? Yeah. So I mean it's a clino amphibole. So therefore you have to think about what are clinopyroxene, and why is the other one a clinopyroxene? Why is the other one an orthopyroxene? Yeah. So and then which cations you can substitute with each other, yeah? So the next question, what physical properties of sheet silicates are related to their crystal structure? So now we are coming to chapter number 5. Here inside this PowerPoint, we are talking about the physical properties of minerals. So, and what are the physical properties of minerals? First, we have the hardness. Second, we have the cleavage. Third, we have the fracture. 4, we have the luster. 5, we have the color. Then we have the strake, and we have the density. And finally the crystal habit. So and here table 3.4 we have something more in detail regarding the physical properties of minerals. So the hardness. So the hardness is controlled by the chemical bonds, and that will result in the hardness of minerals. Covalently bonded minerals are generally harder than ionically bonded minerals. Then we have the cleavage. The cleavage is poor if bonds in crystal structures are strong. Good if bonds are weak. So for example, when you are looking at these sheets, from the sheet silicates, there you have very weak bonds. Covalent bonds generally give a poor or no cleavage. Ionic bonds are weaker and so give a good cleavage. So then we are talking about fracture, and the fracture is related to the distribution of bond strength across irregular surfaces other than cleavage planes. So then we have the luster, and that tends to be glassy for ionically bonded crystals, more variable for covalently bonded crystals. Then we have the color, and that color is determined by ions and trace elements. Many ionically bonded crystals are colorless, and iron tends to color strongly. So then we have the streak, and the streak is the color of fine grained mineral powder, and it is more characteristic than that of massive mineral because of uniformly small size of the grains. Then we have the density, and the density depends on the atomic weight of the atoms which are forming the mineral. Of course, some atoms are more heavy, some atoms are more light. And their closeness of the packing in the crystal structure, yeah, how they are packed to each other, yeah. And that goes then also with the crystallographic symmetries. So then we have the crystal habit, and that depends on the planes of a mineral's crystal structure, and the typical speed and direction of crystal growth. So if we are talking about the hardness, then we can just use here the Mohs scale of the hardness. So the most softest mineral regarding to this hardness scale with the number 1 is the talc. So and that is a very soft mineral, and the other minerals which has also which are falling also on the scale number 1. That is, for example, the graphite or the molybdenum. So then gypsum, we have a hardness of 2, and the gypsum we can scratch with the fingernail. Then we have calcite with a hardness of 3, we can scratch it with a copper coin. We have then a hardness of 4 when we are talking about fluoride. Then we have a scale number of 5 when we are talking about apatite. And the apatite we can scratch with the blade of a knife. Then we have autoclase with a hardness scale of 6. We can scratch it with a window glass, yeah. Then we have quartz with a hardness of 7. You can scratch it with a steel knife, or when you most of the time you do not have a steel knife with you, but some of yours have maybe a Swiss Army knife with them. And with a Swiss Army knife you can scratch it. So then topaz has a hardness of 10. Corundum, which is Al2O3, has a hardness of 9. And the other corundum minerals, you know them, the most common one, that is the sapphire and the rubin, yeah. So and then the hardest mineral, that is the diamond, with a hardness of 10. So then the next point, while we are talking about physical properties of minerals, that is the use of the physical properties. So we are using the physical properties for mineral identification, yeah? So at first, when you are finding a mineral, then you are looking for the color, yeah? I mean, that is the easiest thing, yeah? If it is red, green, blue, or something else. So and then you have already in mind which minerals which minerals are green, which minerals are red, which minerals are blue, and. So but then you need, for a more precise identification, you are using then the hardness and blah blah blah. So and then the use of physical properties for minerals, that is also an industrial application of minerals. So here, for example, we have a Swiss Army knife, which you should have as a geologist, yeah? So, and then we have here, for example, the mica and its cleavage, yeah? So, and here you can see the white mica in front, where the Swiss Army knife is lying on. And in the back you have the biotite. The biotite is the magnesium iron bearing one, whereas the white mica is the aluminium bearing one. And here you can see very nicely all the sheets, yeah? And you can easily go with the knife between these sheets and removing one sheet after the next one, yeah? They are forming such booklets. Then, for example, we have here pyrite, and here the pyrite shows a very nice crystal habit, yeah, which you can see here everywhere on the shape of the crystals. Then here we have a good, very nice example of the cleavage. And here calcite has a very nice cleavage, yeah? And if you are hammering the calcite, then it will always forms, or it will break along this cleavage, and you are getting always these very specific blocks, yeah? With all these specific angles between the planes. So, and here we have a quartz, and the quartz is a hexagonal crystal, and you can see this very nicely. And on the sketch map on the right hand, you can see also the different crystal faces, yeah. And when you are looking from above, then you can turn the quartz crystal 6 times, then it becomes overline by itself. Then we have, for example, the strike, and here we have a hematite, yeah, and the hematite, you know that is Fe2O3, then you are using just such a porcelain plate, and then you can scratch on it, and the hematite will then give a reddish strike. So in there you can then easily distinguish between the hematite and, for example, the magnetite, because the magnetite has a grayish to black strike, whereas the hematite has this reddish strike. Here again some short questions for this chapter. Aragonite with a density of 2.9 gram per cubic centimeter has exactly the same composition as calcite, which has a density of 2.7 gram per cubic centimeter. Other things being equal, which of these two minerals is more likely to have formed under high pressure conditions, yeah? You can just think about it, and then you can just write down your formula, how you are calculating the density, and then you will find the answer. So there are at least 7 physical properties one can use to identify an unknown mineral. Which ones are most useful in discriminating between minerals that look similar? Describe a strategy that would allow you to prove that an unknown clear calcite crystal is not the same mineral as a known clear crystal of quartz. Yeah, just think about, write down an explanation, and send it to me. Here we have some other short questions. Choose 2 minerals from Appendix 4. that you think might make good abrasive and grinding stones for sharpening steel, and describe the physical properties that cause you to believe they would be suitable for that purpose. So just go to Appendix 4 and check which minerals you can use for sharpening steel. So, and then you are describing the physical properties and answer the question and send it back to me. Number 6, what are rocks? So rocks are naturally occurring. These are solid aggregates of minerals, or in some cases non-mineral solid matter. Yeah, as I told you before, using the example no, that was not a good example, or in some cases non-mineral solid matter. The identity is determined by the texture and the composition, and rocks can be classified into 3 groups. We have the igneous rocks, which are magmatic rocks, yeah, and this one you can then subdivide in plutonic and volcanic. Then you have sedimentary rocks, yeah, these are just sediments which has become deposited somewhere and then buried. And you have the metamorphic rocks, which I love most. So, and that is now our next chapter, which we will continue. Maybe I will load up the next video on Sunday. So, and for now you have the first video with audio, and then you can just go through it using the PowerPoint, which I have uploaded on Moodle as well. And then you can just go through the whole thing, answering all the questions, and send then the thought questions back to me. Thank you very much for listening.